Hey everybody, let's talk about the total field solution, the field profile for a circular waveguide in the TE polarization. Now you noticed I've written out the Helmholtz equation in cylindrical coordinates from our last lecture. Okay, so this is our del squared here of hz plus k sub c squared hz, where that cutoff mode number satisfied this condition. Right? And this expression was always true no matter what coordinate system we're in. It's just that if we are in cylindrical coordinate, or we have a cylindrical symmetry on our system, it helps to do the solution in cylindrical coordinates. So, like any good partial differential equation, we are going to assume that the solution is separable, meaning I can apply separation of variables as follows. H sub z of rho comma phi is equal to some function of rho, so r of rho, that's my radial function, and then I will have this other function, p of phi, so p for phi, I guess, is a function of phi. So this is separation of variables at work here, also known as a separable solution to my partial differential equation. So what I'm going to do is just simply substitute that into here. So everywhere you see an hz, you just put an rp, and we don't necessarily have to explicitly write out these dependencies here. We can remember these are functions, and there's going to be another rp for that hz there. And you just carry out all the derivatives on through. So the second partial with respect to rho will imply r double prime p. Then I get plus 1 over rho times the derivative here. So plus 1 over rho r prime p plus 1 over rho squared times r p double prime, so second derivative acting on phi, plus k sub c squared rp is equal to 0. So now we're going to divide everything by rp, and some magic will happen. And it's customary to also kind of multiply by a rho squared while we're at it. So I'm going to basically say rho squared over rp on everything. So this will become rho squared r double prime divided by r plus rho r prime over r plus the rho squareds cancel, and I will get a p double prime over p plus k sub c squared rho squared is equal to 0. So one little quick tricky thing now, I'm going to take this guy here and simply move it over to the other side. So really negative p double prime over p, and then leave that at that. So what I have here, this is all a function of phi on the right-hand side of this equation, and everything else here on the left-hand side is a function of rho. So that argument now implies everything here is a constant, which I am now going to call I'm going to call this positive k sub phi. Okay, I'm going to assume this is a positive because I have the power of foresight. Okay, so here is a function of rho equal to this constant, and there is a function of p also equal to the constant. So let's start by exploring this little differential equation here, which simply evaluates to, we'll say p double prime over p is equal to negative k sub phi squared. And that is a very simple ordinary differential equation, which we can skip right to the solution. P of phi is equal to a sine of k sub phi plus b cosine of k sub phi times phi. Okay, so this is immediately implied by this ordinary differential equation. That is to say, this is the general solution to that differential equation right there. And okay, now where do we go from here? So we now have a separable function, and I have basically figured out the form of this guy here. So the next step is we have to figure out that particular piece of it there. However, before we jump into that, we're going to apply a quick boundary condition on this function here, and that is the following. P of phi is equal to P of phi plus 2 times pi. So this is the periodic boundary condition. Let's say periodic BC. So what that is saying is, if you imagine looking down my waveguide here, so here's a little cross section of my waveguide, right? And there could be some weird field profile in here for my magnetic field, and I pick some random point here. There is some h sub z that corresponds with that point. And if I spin it by 2 pi radians, nothing should change, right? It doesn't make sense to, follow some contour back onto myself and suddenly arrive at a different value. There is only one field value here, and it has to be the same no matter how much I spin around my coordinates here. So what this condition implies, we'll just look at this term here. Sine of, you basically have k sub phi times phi plus k sub phi times 2 times pi is equal to sine of k sub phi times phi. So basically, this is only true. This thing can only ever be a true proposition if k sub phi is an integer. Namely, n equals 0, 1, 2, 3, dot, 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 dot. Okay. Now, the 0 may be a special case that we'll worry about later, but for now, we'll just say any positive or negative integer here is technically allowed for this solution here. So what that implies is everywhere, oh, excuse me, I made a little mistake. There should be a square on that. This over here is just n squared on that little differential equation there for our PDE. So that was pretty straightforward. The angular bit falls out very, very quickly and is not too bad. The difficult part now is going to be how to handle this radial bit. So let's go ahead and figure that out now. Okay, so I have rewritten my differential equation here, because remember, we initially had it set up here, and we had on the right side, we put this p double prime over p, which evaluated to the n squared term over here. Or actually, it was the negative p over p was a positive n squared. Okay, so I've just rewritten this out here. So a quick little rearrangement now. I'm going to rewrite this as rho squared r double prime plus rho r prime plus k sub c squared rho squared minus n squared times r is equal to 0. So I just rewrote this term a little bit. This thing here has a very special name in partial differential equations that is called Bessel's differential equation. Okay, and the solution to it is kind of a giant nightmare. If you took PDEs, you may have been lucky enough to see the solution to this. It's kind of a nasty method that involves an infinite series, kind of like doing a Taylor series expansion. So what you do is you actually don't really solve the function per se. You get a solution in terms of an infinite series, almost like the Taylor series expansion for this R here. And those solutions are called Bessel functions. So what we have is R of rho is equal to Bessel functions. So where's my notes here? There we are. So I get something of the form C j sub n k sub c rho plus d y sub n k sub c rho. Okay, so that is Bessel's equation of the first kind. So I'm going to put a little first, and this guy here is Bessel function of the first kind, and this is the Bessel function of the second kind of order n. So this is not a function that you can calculate using like closed form expressions. They're only solvable using an infinite series, an infinite Taylor series. But for all practical purposes, they are tractable functions. You can just think of this as like a sine and a cosine, or an e to the something, or a tangent. Bessel function, first kind, Bessel function of a second kind. So there shouldn't be anything mystical about them other than what is the algorithm that I have to shove into MATLAB to crunch out numbers for these functions here. So again, hopefully if you've taken PDEs, you've been exposed to it. If you haven't, that's okay. There is a solution that takes you from here to here. It is big and it's ugly, but these functions are the things that solve this equation up here. Now, we're going to apply another quick boundary condition, and I want r of rho to approach 0, or sorry, I want it to, so excuse me, r of rho is finite, not 0, as rho approaches 0. So if you actually plot these two functions, this one is nice and well behaved. This one, however, blows up to infinity at 0. So we therefore say this second kind solution is not allowed. Okay, because it is infinite. It is not a good solution. It will disobey the laws of physics for our particular model, so we reject it as a possible solution. So what we are finally left with is my h sub z is equal to r times p, because we assumed separation of variables, which means I will get something like the following. I get j sub n k sub c rho times a sine of n phi plus b cosine of n phi. So there's my r and there's my phi. And technically, I have to remember that this is an arbitrary constant, but if you multiply it through, you get more arbitrary constants. So we can just imagine that same sort of blob absorbing the c into the a and the b here. Okay, so now the next question is, how do I calculate the a's and b's, and how do I maybe calculate what k sub c is allowed to be? So first things first, let's apply another boundary condition. I need the condition that E sub phi be 0 at rho equals A. So remember, this is simply my tangential electric field must be 0 at the border with any perfect electrical conductor. So we've been using this a lot. This is now our solution here, which is now going to tell us something special about the allowed values for k sub c. So remember, in a previous lecture, we found that if I know what my hz is, I can calculate my e sub rho just fine. And the e to the z isn't going to matter because this will be true at all values of z anyway. So I'm going to just simply go ahead and calculate, my e sub phi, not rho here. So this is the guy I care about here. So I'm going to take the derivative with respect to rho and multiply by this constant here. So E sub phi is equal to plus j omega mu naught over k sub c squared times the partial of h sub z with respect to rho. There we go. Okay, so you notice that just means the derivative with respect to rho means there's going to be a prime here, and then the derivative of the chain rule is going to bring a k sub c out front. So what this is going to end up with, I'm going to get a j omega mu naught. And so that k sub c coming out is actually going to divide out with one of these k sub c's here. So instead of a square, I'll just get a k sub c on the bottom. Then a j sub n prime k sub c rho times a sine n phi plus b cosine n phi, like so. So I want this to be 0 at rho equals a. So I'm going to write this as follows. E sub phi of a comma phi is equal to 0. And that's just going to imply, very quickly, j sub n prime of k sub c times a is equal to 0. So that looks a lot worse than it is. Remember, with the rectangular waveguides, we would get conditions that often looked like sine of k sub x x, or k sub x a is equal to 0, and then we had to calculate the inverse sign of this, right? So you would get k sub x times a is equal to the arc sine of 0, and then you would get k sub x and this evaluated to like n pi stuff. So you get n pi over a like so. The same reasoning applies. The only problem here, the only problem here is I don't know how to calculate an arc derivative Bessel function. There is no real function in MATLAB that kind of does that. It is not something you can calculate using a closed form solution. You have to calculate this numerically, which fortunately our book has done for us already. You just pop open the textbook here. Where's that page? There it is here. So these are the zeros to the derivatives of the Bessel function, which we'll write down here. So a simple notation, your book calls this P sub nm, representing the nth zero for the nth order of a Bessel function. So in other words, if I say j sub n of P sub n m is equal to 0. So this n corresponds with that m, and then there'll be a bunch of zeros corresponding to that. So we'll do some graphs of that in a moment. Then if I do a p prime sub nm, that will correspond to the derivatives of the Bessel function instead. P sub nm prime is equal to 0. So whatever that number is, I'm just defining it as the number such that if I calculate the derivative of the Bessel function at that value, I will get 0. And again, there's no simple closed form way to do it. You just have to graphically solve this thing. But when you figure that out, you finally get the solution that k sub c is equal to p sub nm prime over a. And it's very analogous to this sort of n pi over a thing over here. Okay, so that's what you're seeing here in this table here. N can be 0, 1, 2, and there's the first, second, and the third zeros for these different orders of the Bessel function. And I don't think your book even actually plots them out. So we'll do an exercise where we can visualize this in a bit. But these are the zeros we have to calculate. And don't worry, you won't necessarily have to do them yourself, but we'll just do some table lookups as needed because this is a numerical nightmare. But computers can handle it if you're very clever, and this will tell you the solutions to my circular waveguide. Okay, so at the end of the day, I still have this A and B, and that's okay. These are going to correspond to kind of even and odd symmetries around my waveguide. But that is my solution at the end of the day. So remember now, k sub c squared is equal to k naught squared minus beta squared. So there's going to be an n and an m corresponding to these guys here. So this will imply beta sub nm squared is equal to, or sorry, just the square root, no squared, k naught squared minus this kc squared, which is this nasty thing here, p sub nm prime over a squared. So everything is tractable. This can be calculated in MATLAB, no problem. It's just a simple function called Bessel J. And you can give it the order and then the argument there. So that's no problem. There are simple rules for calculating these derivatives in MATLAB as well, using some clever identities. This thing, however, here is the monster. How do I numerically calculate these zeros? And the answer is basically you gotta just do it graphically. So if I were to plot the Bessel functions and its derivatives, it sort of looks like these sort of exponentially decaying sinusoidal things, but they're not at regular intervals. So if I write j sub n prime a row like that, and you have to calculate these zeros using just numerical methods, and it sucks. So we'll do our best to try and keep that reasonable on our homework problems, but that little constant there is the nightmare when it comes to solving the field profiles within a circular waveguide. But other than that, everything is pretty well easily tractable. So there you go. That's the full solution for the Z component of my magnetic field in a circular waveguide. And if we also remember, if once I have that solution, I can then apply these formulas to get all of the other field components in cylindrical coordinates.